Picture this for a moment, a bustling city, streets filled with people going about their day, markets, schools, homes with families inside, children playing, the hum of daily life all around. Now picture all of that not on Earth but on Mars, the red planet. A world that for centuries belonged only to telescopes, science fiction novels, and the wildest dreams of humanity. What once seemed like pure fantasy is no longer just imagination, it is slowly becoming our reality. And the man behind this audacious dream, Elon Musk. His vision is breathtaking in its scale. He wants to build the first self-sustaining city on Mars before the year 2050, not a small research outpost, not a temporary base, a real, functioning, independent city, a place where humans live, work, raise families, and thrive, a second home for our species. But here is the thing, dreams of this magnitude do not come cheap and they do not come easy. To make Mars a habitable world for humans, SpaceX needs something almost unthinkable. They need to produce between 800 and 1,000 Starships every single year, for 10 straight years. That would create a massive construction fleet capable of ferrying the materials, equipment, and people needed to build a city from scratch on another planet, and building that city itself. That alone is expected to take around 20 years. It sounds impossible, it sounds insane, and yet Musk is so confident in this dream that he has publicly guaranteed it will happen in the not-too-distant future. The engineers at SpaceX are working day and night around the clock, pushing the boundaries of what is technically possible. Their focus is sharp. Their mission is clear: speed up the development of Starship and the Raptor engine that powers it. And the progress has been so remarkable that even seasoned space industry veterans cannot hide their amazement. One official from NASA could not help but express genuine astonishment, saying that SpaceX builds these machines at a pace nobody has ever seen before. Their initial target was 7 engines per week. And not only did they hit that target, they hit it a full quarter ahead of schedule. 7 engines every week. That breaks down to roughly 1 engine every single day. For anyone who understands rocket science, this is nothing short of unbelievable. But here is where it gets even crazier. 7 engines per week is not the finish line. It is barely the starting point. Elon Musk wants more, much more. He expects production to reach 2 to 4 Raptor engines per day. That means doubling or even quadrupling the current speed. Why? Because anything less simply will not be enough to meet the ambitious goal of producing up to 1,000 Starships per year. So the question burning in everyone's mind is this: How does a company manage to ramp up production of one of the most complex machines ever engineered to such an extraordinary pace? Let us walk through it together. The first piece of the puzzle is something called iteration. The fastest way to mass produce a Raptor engine is to iterate quickly and efficiently. This means making something, testing it, learning from it, breaking it if needed, and then making it again, but better. Every cycle teaches the engineers something new. The huge advantage of this approach is that it creates endless opportunities to experiment and to fail. And failure, surprisingly, is one of the most valuable tools in engineering. Think about the upgrade journey from Raptor V1 to V2 to the current V3. Each transition required thousands upon thousands of tests on the ground and in the sky. Without a steady supply of engines, you simply cannot run that many tests. You become hesitant, you hold back, you play it too safe. You stop daring to push limits or blow things up to learn what went wrong. And the moment you stop daring, innovation dies. Less experience means fewer breakthroughs. Iteration also dramatically cuts production time. Once you have built something successfully, copying it becomes faster, smoother, and cheaper. Engineers save time, they save effort, they save money. And that explains why everything inside SpaceX moves at, well, rocket speed. But just copying is not enough. Musk has also focused intensely on evolving the design of the Raptor itself. The goal is to make it lighter, simpler, easier to manufacture, and cheaper to produce. Looking at the evolution from V1 to V2 makes this clear. The second version cut away a huge amount of complexity. SpaceX eliminated a vast maze of primary, secondary, and tertiary plumbing. By 2022, Musk confirmed that they had even removed the complex torch igniter system from the main combustion chamber. All these changes made Raptor V2 dramatically easier to build, and the production numbers prove it. What makes it even more impressive is that despite removing so much complexity, the engineers managed to increase thrust by 25%, sacrificing only 1% of efficiency. There is another fascinating shift. Musk wants to reduce the use of 3D printing as much as possible. This might sound surprising because 3D printing is often praised as cutting edge, but it has real downsides too. It can be expensive and it slows down production. Simpler design also slashes cost. Raptor V2 is expected to cost around $1,000 per ton of thrust, which works out to about $230,000 for an engine producing 230 tons of thrust. Compare that to the early Raptor V1 prototypes, where each engine cost over $2 million for just 185 tons of thrust. That is roughly $11,000 per ton. The drop in cost is staggering. Beyond cost and design, durability is critical. Most of the metal components are made from special alloys. Currently, a material called SX300 is used, and a more advanced version called SX500 is in development. Musk described SX500 as a superalloy capable of handling 12,000 psi of oxygen-rich hot gas, conditions in which almost every other metal would catch fire. Both alloys are single-crystal superalloys, essentially modern versions of Inconel alloys. These are already used in extreme industrial environments like gas turbines for power plants and jet engines. But for the most powerful rocket engine ever built, the materials need to go even further. Musk wants SpaceX to develop its own versions to build incredibly reliable, rugged turbopumps for the Raptor. And then there is the production muscle behind all of this. SpaceX completed a second manufacturing facility in McGregor, Texas, sitting on 4,280 acres of land roughly halfway between Dallas and Austin, just south of Waco. This cutting-edge factory is built to mass-produce between 800 and 1,000 Raptor V2 engines per year. Meanwhile, Raptor vacuum production stays at the Hawthorne, California headquarters, alongside experimental new designs. Ground was broken in July 2021, and by 2022 the facility was operational. By November of that same year, the 200th Raptor V2 engine rolled out, all produced at the McGregor site, 200 engines in just a few months. The pace is breathtaking. Producing and testing engines in the same location cuts down massively on time and transportation costs. It accelerates everything. In short, SpaceX has every condition in place to push Raptor production to the level Musk dreams of. And once that happens, Starship will be ready for its full high-cadence flight schedule. That is what shortens the road from Earth to Mars. That is what helps America stay ahead in the new space race against China. Compare this with the RS-25 engine used on NASA's SLS rocket. In 2015, NASA awarded Aerojet Rocketdyne a $1.16 billion contract just to restart production. That money was only to set up the facilities, not to build the engines. Each engine then costs over $100 million, and the goal is just 4 engines per year. Painfully slow compared to SpaceX's pace, and barely enough to keep up with global demand, especially with China planning to land astronauts on the moon before 2030. All eyes now turn to Elon Musk. The future of human space travel may very well rest on his shoulders, and the next few years will reveal just how close that Martian dream really is.